Alright, hello everyone. Welcome to my channel. And this is an educational channel. We're going to be looking at, well, in general, we look at theories of everything and things that can improve your life in every aspect if you were privy to them. And today is video number 316 that we have done on Dewey B. Larson's reciprocal system of theory. And Mr. Larson was an engineer who lived in the 20th century, born in North Dakota in 1898, died in 1990. He moved out west. He was a World War I vet, and then he moved out west to Oregon, went to college out there, and became an engineer at I think a mining engineer in Portland, and stumbled across, was working on some smaller problems, trying to make some advancements, but stumbled across you know, some kind of eye-opening things, and pursued them to their ends, and ended up developing a full-blown theory of everything, a system of theory. Basically, he has set up two postulates, and from there he derives an entire theoretical universe, and from that universe he wrote books on all kinds of different subjects, including chemistry and physics and astronomy, but also even some economics and some of the social sciences, or even the liberal arts. And the basic idea behind Larson's theory is that we live in a universe made out of motion. Not matter and not energy, but motion. For Larson, motion was the relationship between space and time. And space and time both have three dimensions. Because they are reciprocals of each other, they have identical qualities. Space and time are basically two components of the numerator and denominator of a fraction that is motion. So motion is you know, some kind of permutation of time over space or space over time. But they come in multiple dimensions: coordinate space and coordinate time. And then they're also progressing, what Larson calls clock space and clock time. The clock, with the clock, the time is always getting later and later and later and later. And with clock space, the space is always getting farther and farther and farther apart. And then space and time are also both quantized, meaning that they have there is a minimum unit of space and a minimum unit of time. If you don't have a full unit, then you don't have, if you don't have a full unit of space, then you don't have space. And by a corollary, then you only have time, because the universe is made out of space, time, or motion. And so it's got to be one or the other or both. So if you don't have space, then you only have time. Larson calls that the time region. And if you don't have time, then because you don't have a full unit of it, if you have less than one unit, then you only have space. Larson calls that the space region. And between those two, you have what Larson calls unit speed, 1 unit of space in 1 unit of time. Space over time is speed, and 1 over 1 equals 1. This unit speed is the speed of light. So in Larson's system, the speed of light is really the background or the reference point, the 0 point, the null point, the origin, the ether of the universe. And half of the universe is moving actually faster than the speed of light. which flies in the face of Einstein's dictum that says that the universe, the speed limit of the universe is the speed of light. That's only true for what Larson calls the material sector, that sector of the universe that's moving faster than the speed of light. But in the cosmic sector, the sector moving faster than the speed of light, that doesn't pertain to that. That's part of the universe that Einstein didn't know anything about. So he took that postulate. The second postulate is basically that the universe conforms to the rules of ordinary mathematics. Its primary magnitudes are absolute, and its geometry is Euclidean. And that actually is under some dispute by some of his followers. But the first postulate is the main gist of it. And then he derived a theoretical universe from that. We're looking at an article that he wrote, I think it's a paper that he gave back in the early 1980s, that is called Scalar Motion. And I believe this is the fourth installment of that. And so if you want to get start at the beginning, you want to go back about 3 episodes and listen from there. So we're taking over kind of in the middle of the article. Larson talks about scalar motion. Now, scalar motion is a motion that has a magnitude, but it has no specific direction, like a clock or like a balloon with spots on it. You blow up the balloon, all the spots are moving away from each other, but in no specific direction. You suck in the balloon, all the spots are moving toward each other, but in no specific direction. Really, the only direction of scalar motion is either in or out. And that would be like time, space, the progression of space. Now, that progression of space obtains in the cosmic sector. So in the cosmic sector, you have coordinate time and clock space. Those are unfamiliar to us in general. But in the material sector, we're much more familiar with that. That is coordinate space and clock time. And Larson is talking about how scalar motion is a bona fide aspect of the universe, and that, scientists know all about it. The Hubble telescope identified that the distant galaxies are all moving away from each other, but they haven't determined the significance of scalar motion. And so Larson is giving it its significance, especially a kind of motion that he calls a distributed scalar motion, which is really, if you take that balloon that's expanding and then you also rotate it at the same time, then you would have what he calls a distributed scalar motion. And he says that, a one-dimensional distributed scalar motion is a charge. A two-dimensional distributed scalar motion, an electric charge. A two-dimensional distributed scalar motion is a magnetic charge, and a three-dimensional distributed scalar motion is gravitational charge. He is basically saying that you need 3 dimensions of space in order to define a one-dimensional scalar motion. So that there is a lot of motion in scalar, because scalar motion has 3 dimensions. So there are 2 other dimensions of scalar motion that cannot be described in the reference system, in our XYZ coordinates. our XYZ coordinates are only capable of representing one dimension of scalar motion. Okay, let's start up right here. An increase in the time while the space is constant results in a decrease in space per unit time, and therefore causes a change of position in space. An increase in space with time remaining constant decreases time per unit space and causes a change of position in time. So here we arrive at the concept of motion in time. This concept is perfectly familiar to those of you who have been dealing with the theory of the universe of motion, and a great deal of what I am saying now is very much the same as what I was saying years ago when I was first explaining that theory. So it's old stuff to you, but it has quite different significance in the present context. The extent to which we can now derive these conclusions from established facts greatly strengthens the position of the theory. Many individuals have rejected our conclusions without any serious consideration, simply because they conflict with ideas of long standing that have had no basis other than assumptions to begin with. But now that we are able to show that these conclusions are consequences of positively established facts, that option, as I said with regard to another item, is no longer open. Scientists have no option but to accommodate themselves to the facts. You would think, anyway. The system of scalar motions that we can represent in the spatial reference system, the one-dimensional motion that I was talking about earlier, can be duplicated in time because of this space-time symmetry, so that we have another system equivalent to the scalar motion system that is represented in our reference frame. The derivation that I am giving you now deals only with scalar motion, and we'll have to leave vectorial motion for consideration at some other time, because I haven't brought that within the factual limits yet. But we can consider this point that gravitation is a scalar motion, and that consequently all gravitating objects are included in the inverse system. This includes all material objects. It follows that the inverse system is at least coextensive with the system that is open to observation, whether or not it is an exact duplicate. The inverse system that I have been talking about is a system of maximum speed, the system that we are well acquainted with, that we deal with on our ordinary reference system, is a system of minimum speed. Now, I want to take a brief look at some of the things that happen in the intervening area. First, we need to look at some of the primary processes that are involved. The progression of the natural reference system is outward, a plus or positive motion in our usual language. It is limited to 1 unit because that is the maximum that we can have in a system of discrete units. Gravitation is capable of extending to 2 units before it reaches a net resultant of 1 negative unit. So from positive 1 to negative 1, I believe is what he's saying. And to that 1 negative unit, we can apply outward translational motion in 1 dimension. Here we again have a range of 2 units, and that is from negative 1 unit to positive 1 unit. The same is true in each of the 3 dimensions. That gives us a total separation of 6 units of speed from 1, 0 to the other, from the zero in the material sector to the zero in the cosmic sector, I think. So far, I have been talking about full units. Of course, when we exclude fractional units, we don't have anything but full units. But we can produce the equivalent of a fractional unit by adding units of the opposite kind. That is, units of motion in time. N units of motion in time are equivalent to minus 1 over n units of motion in space, so that we accomplish a resultant of less than 1 unit by combining one full unit with the oppositely directed fractional unit from the other direction. This is the first speed range, the range from 0 to 1 unit. It is the range of our ordinary experience, the speed range that's represented in the spatial reference system. It's not possible, obviously, to exceed 1 unit by any kind of a subtraction from a single unit, which accounts for the limitation on the speed in one dimension. But there is nothing to prevent the addition of another full unit, so that in the next speed range we have 2 units minus a fractional unit. The same is true in the third speed range. It's necessary to keep in mind that the first of the 2 units is a unit of space, and that there is a unit of time in the same dimension. There is a unit of space from 0 space to unity, which is the unit of both space and time, and another unit from this unit level to 0 time, as opposed to 0 space. Thus, the second unit of motion is in time. Then, in order to add a third unit, we have to go to a second dimension, so that again we have a dimension of space. On this basis, the speed from 0 to 1 unit is in space. That's the ordinary motion that we are acquainted with. A speed from 1 unit to 2 units is in the same dimension, but it is in time. So this is the second dimension of motion he's talking about here. A speed from 2 units to 3 units constitutes that unit of speed in time, but adds a unit of speed in space, so that it's 2-dimensional. These are the major characteristics of high-speed motion as we derive them from the reciprocal relationship that we have just found. In order to give a meaning in terms of our physical observations, we have to resort to the identification process again. The most energetic processes that we know of in the universe are explosions of stars and galaxies. If any objects with speeds in these intermediate ranges that I have been talking about actually exist, they must exist as objects of that kind. So let's look at them. All violent explosions generate some low-speed products, and we see those low-speed products expanding away from the site of the explosion, usually at high speeds. Those products are not of particular interest to us now because they are in the lower speed range. I mean, he just got done saying, from the site of the explosion, usually at high speeds. And in the next sentence he says, those products are not of particular interest to us now because they are in the lower speed range. But that's what he means. They are in the lower speed range, meaning that they are less than the speed of light, less than unit speed, but they are at high speeds, because they are very fast from our normal reference system. They're just not at the speed of light, but they're very fast. So he's just tripping over his own words right here and making it just utterly ambiguous all over the place. This is a very important passage. I mean, what I've been reading this whole day here is very important, but it's really difficult to extract the information, at least for me, on this. So we'll go back to the beginning of the sentence. Those products are not of particular interest to us now because they are in the lower speed range, the ordinary speeds of our everyday experience. But in motion in the second speed range, the change of position is in time. So that the motion in that speed range produces the same kind of a cloud of expanding particles, but this time they are expanding into time. Because of the reciprocal relation between space and time that I have been just talking about, the cloud of particles expanding into time decreases in size as seen in the spatial reference system. So that we observe such a cloud of particles as a very small object of very high density, which remains in essentially the original location. And such an object can, of course, be identified with the stars that we know as white dwarfs. So here, then, we can identify objects in which the speeds are in the second speed range, from unity to 2 units. This is another conclusion we reached theoretically, but now we find that we have sufficient evidence to establish it as a consequence of positively established facts. We also have evidence that there are explosions of galaxies, and since these are very much larger objects, our own galaxy contains something like 10 to the 11th power solar masses, 100 billion times the size of one star. The explosion of a galaxy is very much more violent, and we can therefore deduce that some of the products of that explosion will probably enter the third speed range. As I pointed out a short time ago, that should have 2 consequences. Because it has a 2-dimensional motion, it's in the second dimension of speed. One dimension of which is in time and another in space. That kind of an object will be moving rapidly outward as well as decreasing in size, like the white dwarf star. Such an object will therefore be the equivalent of what we might call a white dwarf galaxy. Not a galaxy composed of white dwarf stars, but a galaxy that has the properties of white dwarfs. We can easily identify this as one of the objects known as quasars. Now, to summarize what I said, I have not been able to find the kind of a crucial experiment that I and others have been looking for, but by means of a systematic analysis of previous experimental work, I have uncovered 2 hitherto unrecognized facts of a crucial nature, the kind of facts that would have been obtained from crucial experiments if I had found such an experiment or 2 of them. These new crucial facts are, first, the existence of distributed scalar motion, and second, the limitation of all scalar motion to discrete units. With the benefit of these new critical items of information, many of the unique features of a universe of motion, including multidimensional motion, motion in time, speeds greater than that of light, and a second half of the universe, can now be presented to the scientific community as established facts, rather than as theoretical speculations. This should aid very materially in the continuing effort to secure the serious consideration that has thus far been so difficult to obtain. Okay, now that is the end of that article. That information, the information is there. It's all there. At least the way I understand the reciprocal system, he summarizes it there. It's difficult to extract the information from that article. You may need to listen to this video a few times over before you get it. I'm going to, at some point when I get time, which is hard to come by, to try to kind of reformulate some of these positions of Larson into a language that maybe at least will be more amenable to me, and hopefully will be to you as well. Because I know Larson says what he means and he means what he says, but sometimes things get ambiguous, and I know it's not completely his fault. I believe he's a good writer, but, you know, he's having to identify so many new concepts and, you know, use different words in different ways, and it's very difficult for him to establish a language that everybody can really understand. I don't believe that it's really Larson's fault. It's really the public's fault for, you know, kind of not being exposed to you know, different ways of speaking and different nuances of language, and also not really being very willing to persevere to actually figure out what he means, and instead just assuming that he means nothing, or nonsense, or gibberish, and or just being inconsistent. He's consistent with the language that he uses, but sometimes he uses two words to express the same thing, and some words that he uses are sticky. That, you know, dimension and direction. These kind of words sometimes have double meanings, and like I said, I don't think it's all his fault. If you blame him, you're expecting too much, because I mean, what do you want from the guy? He came up with a theory of everything, you know, a theory of how everything in the universe operates, and it's logical and consistent. He's just one guy. He didn't have, you know, he didn't have an army of researchers behind him checking his work and proofreading his papers. He didn't have, you know, graduate students or whatever working for him. He didn't have any of those benefits. He was pretty much doing this on his own. So I give him credit, and, you know, you just have to kind of put up with some of the difficulties and try to persevere through them. So hopefully you'll do that, and hopefully I will also be able to help out a little bit as a person who I think knows what he means, but sometimes I might see that he doesn't exactly get to the main point of what he's trying to say. Okay, thanks for tuning in today, and we will see you tomorrow. Have a great night.